magnetic field is applied to a particular type of material, that is a superconducting material, it should be under some particular conditions. Suppose a material is under a condition where its applied critical field is higher, or applied field is higher than its critical field, and applied temperature is higher than its critical temperature, then the flux line which is passing through unit cross section area will not be equal to 0. That means flux line per unit area can easily pass when the field or the applied field is higher than the critical field and the applied temperature is higher than the critical temperature. In the same manner, if we bring down the material at the temperature which is less than the critical temperature or at a particular critical temperature, we know that below critical temperature or at a critical temperature the material behaves as a superconductor. That means if the applied field on that material is less than the critical field and the applied temperature is less than the critical temperature, what will happen is the material will start behaving as a superconducting material. Under this condition, what we will observe, let me show you through a figure. Here in our next slide you can see two types of condition. In your first condition you can see that the arrows are passing through that circle. The circle is a type of a material and arrows are passing through that material. You can see or you can observe that arrows are passing through that material. And the above given conditions are the field is greater than the critical field and the temperature is greater than the critical temperature. Means what? The green circle which you observe is the material, which is a normal material under this condition. When field are greater than critical field and temperature are greater than critical temperature, that material will behave as a normal material. That means what? The value of flux line passing through unit area will not be 0. That means flux line can pass in the first condition. Now you can see in the second diagram, the flux line are not able to pass through that circle. That means that circle is a type of material which is under some certain conditions. The conditions are the field applied on it is less than critical field and the temperature applied is less than critical temperature. The thing happens is under critical temperature or the temperature below critical temperature, the material behaves as a superconductor. You can observe that the circle is a material and when you apply temperature below critical temperature, what will happen is the field will oppose the applied field. My friends, in this diagram the arrows are representing the applied magnetic field. When applied magnetic field H is represented, when under critical field, what will happen? The material will oppose the applied magnetic field. Actually, what is happening in the second condition is that there will be generation of a surface current which will lead to magnetization, and this magnetization will be equal to the applied magnetic field. But actually what is happening is inside the material the applied field and the generated magnetization is opposite to each other. Though they are equal, but they are opposite to each other. So due to which inside the material or inside your second diagram, what will happen? That the effect of the magnetization will be nullified. That means not a single flux line, or I can say not a single magnetic flux will pass through that material. So it can be represented in words. We will observe that words in our slide. Let us read it according to the definition. The above process occurs due to development of surface current, which in turn results in the development of magnetization within the superconducting material. That means when you apply a magnetic field on a particular type of superconducting material, there will be a development of surface current, which in turn results in the development of magnetization. That means surface currents are responsible for the magnetization generated inside the material, or we can say superconducting material, because the material is under critical temperature condition. As the development of magnetization and applied magnetic field are equal in magnitude, that means the value of magnetic field and magnetization becomes equal, but they are opposite in direction. So they cancel each other everywhere inside the material. And if I say flux line passing through unit area will become equal to 0, and the condition in our above diagram will be diamagnetic. That means the second sphere under critical temperature condition will behave as a diamagnetic material, or superconducting state will achieve a diamagnetic state. Let us move towards the third question. Calculate the critical current for a superconducting wire of lead having diameter of 1 mm at 4.2 Kelvin temperature. Critical temperature for lead is 7.18 Kelvin and critical field at 0 Kelvin temperature is 6.5 into 10 raised to 4 ampere per meter. Now we have some conditions. We have to calculate critical current for a superconducting wire of lead. That means lead is a type of material through which a superconducting wire is prepared, and we have to calculate the critical current of that superconducting wire which is prepared from lead. The diameter of that superconducting wire is 1 mm, which is at 4.2 Kelvin temperature. Critical temperature for lead is given, that is 7.18 Kelvin, and H0 is 6.5 into 10 raised to 4 ampere per meter. So we have to calculate the critical current where there is a particular temperature of 4.2 Kelvin. Okay, so let us calculate this. Let us move towards the next slide. Here you can see the equation that Hc is equal to H0 into 1 minus T square upon Tc square. Actually it is T upon Tc whole square. You can also write that T square upon Tc square. Here directly I have written the calculated value of critical field, that is 42.758 ampere per meter, by substituting the values. IC is the value of critical current, which is equal to 2 pi R Hc. Let me represent the first equation, which is in blue color. Hc is the critical field at a particular temperature, or if I say critical field at a particular temperature, H0 is the particular critical field at 0 Kelvin temperature. So if I represent the second equation, IC is the critical current, R is the radius, and Hc is the critical field. Let me show you that how we have substituted the values on this board. Here the equation is Hc is equal to H0 into 1 minus T upon Tc raised to whole square. This is the main equation. Let me show you the values. The diameter is of 1 millimeter. The diameter is equal to 1 millimeter. That means the radius will be half of it. We need to calculate critical current, and critical current is equal to 2 pi r into Hc. To calculate the critical current, we have to substitute the value of R and to substitute the value of Hc. So we have already given the value of H0, we have given the value of T, that is 4.2 Kelvin, and the value of Tc, that is 7.18 Kelvin. By substituting these three values, we can calculate the critical field. By calculating the critical field, we can substitute this value in this equation, and by substituting this equation, by substituting the value of Hc, we can calculate the Ic, that is critical current. So in our slide, Hc is equal to H0 into 1 minus T square upon Tc square is the equation to calculate critical field at a particular temperature T, and by substituting the values of Hc, here you can see that we have calculated Hc by substituting the values of H0, T and Tc. By substituting this value, we can calculate Hc, and by substituting Hc in this equation, we can calculate Ic. That is what you call the critical current. Now let us go towards the next question. Discuss the properties of laser in detail. What do you mean by laser? Here it is represented as light amplification by the stimulated emission of radiation. This is the full form of laser. I repeat, light amplification by the stimulated emission of radiation. Through a stimulated emission, or by getting the stimulated type of emission, we can amplify the light signal and get a higher energy light rays. And these light rays of higher energy content, which are directional, having higher intensity, that means per unit area the energy content is higher, it is coherence, that is in same phase, and it is monochromatic. Here mono represents one as well as chromatic represents color. That means the laser is of a single color. We have to discuss about the properties of laser. There are 4 properties of laser. First one is coherence, second one is high intensity, third one is high directional, and fourth one is high monochromatic. Coherence, let us represent about coherence. This is the first point. Coherence, the wave train which are identical in phase and direction are called coherent waves. That means the wave trains, these words are used for many waves. That means waves or serial waves which are identical in phase. That means they are identical, their phase are identical, means two different waves are having same phase and having the same direction. And if this occurs, that means waves are having same phase and same direction, these waves are coherent. all the constituent photons of laser beam possesses the same energy, momentum, and they propagates in the same direction as in the form of a beam, and this type of a beam is said to be coherent. Let us move towards the next point, or if I say next property, that is high intensity. But before that, I have represented a diagram. You can see a bulb there and you can see a laser there. The coherent waves represents the same phase in a single direction, whereas the light which is getting emitted from a lamp is not directional, it is scattering. That means it is scattering in all direction or moving in all direction. It is not necessary that it is having same phase. So in comparison to laser, it is having no same phase. That means they are not coherent waves. Laser are having a coherence nature. Let us move towards the next slide, high intensity. That means energy per unit area is higher. Due to the coherent nature of laser, it has the ability to focus over a small area of 10 raised to minus 6 centimeter square. What does it represents? It represents that 10 raised to minus 6 centimeter square is a very small area, and the laser light can be focused over a very small area of 10 raised to minus 6 centimeter square. That is extremely high concentration of energy over a small area is possible. My dear friends, the application of laser is welding, cutting, drilling. To drill or to make a hole, a high energy content of light is possible. We can say that normal light is not able to concentrate at a particular smaller area in comparison to laser. So let us move to next point, directional. An ordinary source emit light in all possible directions. That means ordinary light spreads in all possible directions,